Welcome you all to the course on machine learning. In today's session, we will be talking about a gradient descent or the steepest descent, or I could say that the learning rule, how the mathematical model which uses for optimization techniques, which learns the learning rate. The previous model or the previous lectures, we discussed about the introduction to the optimization. Also, we discussed about the few mathematics or the functions or the logics behind or mathematic derivatives behind the steepest descents. In today's session, we will talk about or we will discuss about some numericals, which through we will understand how we can able to find out the optimal solution using the steepest descent method. This is the diagram, and we are talking about the optimization. Optimization is the function through which we will try to find out the optimal solution or the better solution to the given problem. So here, so that the optimization that may involve to finding out the maximum output or the maximum performance or other ways that could be represented in terms of the minimum errors. So we may maximize something or we can minimize something. Here the maximization which may involves maximizing the performance as well as minimization again in terms of the errors. In the previous lesson we discussed about how we can able to find out the mean squared errors and what are the steps we supposed to do to reduce the errors that we discussed with that how we can able to find out the optimal weight when we are trying to train our the neural network model. Very similar to that, when we talk about the gradient based methods, right? See, we discussed about the objective function as well as the constraint and then the various, right? So when we talk about the objective function through which we will try to find out the optimal solutions. When we talk about the variables, the different inputs which will pass to the objective functions. When you talk about the constraints, right? Whatever the equations which we uses to find out the optimal solutions, so that becomes the variance, right? When we talk about the gradient of the objective function has very important property that if we move along the gradient direction from any point, the function value increases at the faster rate. So in yesterday's lecture we discussed about that we seen a diagram that so in that so I need to move from one point to other point. So that red dot, which was my the objective function, that goal, right? I'm standing somewhere in between, but my option is that whether I may go upward or I may go downwards. I have to, but I don't know in which direction I supposed to move. But initially, I can try either direction, and then I'll try to find out the error whether my distance has been increased or decreased. Then, based on that calculation analysis, and then move in the different directions. Very similar to that. So here, as per this diagram, which is illustrated here, the gradient direction, which is known as the direction of the steepest ascent or descents, right here in the different the points which I represents that point 1, 2, 3, 4 are the steps or the points through which instead of going in the straight direction I can move into the step by step. I can reach I can find out the first the local optimum or the local optimum, and then I can move along with the direction so that step by step I will find out the optimal solutions and then I can reach my goal. When we talk about the different steps which involved in the steepest descent are the Cauchy method, the first thing is that we need to find or we need to set that arbitrary initial point which is capital X1. Consider the iteration number which is represented by it. So initially, so we are going to set or we are going to initialize some the initial point which could be 0, 0 or any numerical numbers, and then we are going to set the iteration number. So because so here we need to repeat so many steps, then only we will be able to find out the optimal solution, whether we may reach the optimal point at the first step itself or we may further that step which has to be repeated so many steps, so that after some steps and we may find out the final steps are the optimal solution. Now the second step is that find the search direction Si, which is given in the equations. Si is equal to minus delta Fi, and which is equal to minus delta F of Xi. So here this is what the function or search direction function through which we will be able to find out in which direction we have to move to our optimal solution, or we can find out are the objective functions. And the third point, once we find out the optimal search direction, and then the third step, we need to find out the optimal step length. So this is again in terms of distance, which is lambda I in the direction of si. Si is already we discussed about the direction in which we supposed to move. Once we found out the direction, and then we will try to find out that the step length we supposed to move, that is represented in terms of lambda I. X of I plus 1 is equal to next step from our the current step, which is equal to xi plus lambda I and then s1. So here the si which is represent the direction, and then lambda I which is represent the length we supposed to take care, I mean the length we supposed to move, and xi is the current place. So when we talk about this, from our current position we need to move this lambda I length in the direction of si. So that is equal to xi current, current position minus lambda I and then this delta f. So delta f which is represented again with this formula. Now, once if you use found out this value, x of I plus 1, right? To test the new point x of I plus 1 for optimally condition whose derivative equal to 0, and then whatever the results we are going to get, and we are going to check that whether the results what we derived which is equal to 0. In other words, check if the new points is lesser than the previous one. If it is less, then we are going to check whether the distance is increasing or decreasing. If it is lesser, then the direction of the movement is ideal. That means that we are moving in the right directions, and becomes, and after some point x of I plus 1 becomes the optimum point. So if x of I plus 1 is the optimum point, then stop process, otherwise we go to step 5. So here the step 5 means again we need to repeat the process. And able to understand? So here what we are going to do is that, so here the through this step, third step, right, we are going to find out the next step in which direction we have to move. Xi is the current position, and lambda is equal to the length we supposed to move. Si is the direction. Once if you are moving the particular distance in the particular direction, then we have to check that whether we have reached the results whatever we moved, whether it is increased or decreased. Then if it is less, then we are keep on moving the same direction. If it is increased, again we have to take it in the reverse way. So finally, we will reach the optimal solutions if you are getting the continuous results, or if the results are unchanged, or if you are getting the optimal value which is equal to 0 0, then that means that we have reached our optimal point. The final step is that set the new iterations which is I is equal to I plus 1, and then go to step number 2. Step number 2 again for searching the direction, and then we supposed to repeat it. We need to find out the direction and then length, and then we need to find out the optimal value. So this is what the different steps which involves in the steepest descent using the Cauchy method. Now we will take a numerical example, and then we will try to find out the optimal solution or optimal point for the given quadratic equations. When we talk about, this is the given equation which is minimize f of x1 comma x2. So these consist of two variables, and the equation which is given 4x1 minus 2 plus 2x1 square plus 2x1 x2 plus x2 square, and then starting from the point x1 which is equal to 0 0 0. So in the previous slide we discussed about that the first point is that in order to find out the optimal solution, we need to set, or we need to find the initial values. So for this given problem, they have given the initial values which are 0 0. Now what we are going to do is that we are going to set the values for x1 and x2. So here the x1 and x2, they have given the variables and values, they have given the initial value which is 0 0. Now what we are going to do is that in that given equation, so now we are going to set the x1 x2 value, and then we are going to do that the differentiation with this the delta f, right? When you talk about this, the delta f which is given dou f by dou x1, the given equation that should be differentiated with the x1. So when we are differentiating with that x1, so here we will get 4x1, here we will get 4, and then minus 2x2, this is a constant value, right? Again the 2x1 square which will becomes a 4x1, and then 2x1 x2, so here x1 will get vanished, and then so here we'll get to x2. Now this is the x2 square again, which will be a constant. Again, the second function in which we are trying to differentiate the x with the x2, dou f with respect to the dou x2. Now when you are doing it, so now again this is the constant value which will be neglected again. So here we will get minus 2 if you differentiate minus 2 x2. So here we will get minus 2, and so here again this is the constant value. So here we will get 2x1, and then so here x2 square we will get 2x2. Now, once if we get this value, after that, if you are substituting out the values 0, comma 0 in this equation, so here if I substitute my x1 value which is equal to 0, and then x2 value is equal to 0, all these terms will get vanished. This and this. So here I'll get only the two elements delta f of x1, which is 4, and then minus 2. But in the second step what we need to do is that we need to find out the direction, which is minus delta f5, in which so automatically the sign of the 2 value which is going to change. So here the 4 will become minus 4, again the 2 will become the sorry minus 2 will become plus 2, right? In the third step is that what was our third step? In the third step we need to find out the optimal step length, which is lambda 1. That was the component in which we are supposed to find out in the direction of SI. We calculated that S1 which is equal to minus 4 and then 2, right? And that we need to find out the lambda value, which is the step length in the direction of SI. So again, which will be represented using that f of minus lambda I comma lambda I. So here if you move into this step, so here this is what the function which is given x1, which is the current position, plus lambda 1, and then si. Lambda 1 is the step length, and then si is the point which we calculated in the step number 2, which is xi is the initial values, the initial coordinate which we the given in the problem, which is 0 0 plus lambda 1. That is what we are going to find out in the step 3. And then so this s1 value which we calculated, which is minus 4 and then 2. If we simplify these equations and substituting it, right? So here what I am going to do is that, so here minus 4 lambda I and then 2 lambda 1. So here that I am going to substitute here this, instead of, if I use this f of x1 comma x2 using that the step 3, so here the x1 value which will become the minus lambda, and then x2 value which will be the plus lambda. And if I substitute the values into this equation, what was the value, which is x1 equal to minus lambda, and then the x2 is equal to plus lambda. I'll substitute this value minus 4 lambda 1, and then minus 2 lambda 1, and then 2 lambda 1 square minus 2 lambda 1, and then plus lambda 1 square. If I simplify it, what I will get it, right? So this 2 value which I will added, minus 4 lambda 1 minus 2 lambda 1, which I will get minus 6 lambda 1. So here 2 lambda 1 square. So here I will get minus 2 lambda 1 multiplied by lambda 1. So here I will get minus 2 lambda 1 square. So these two terms will get vanished. Again the lambda 1 square. If I simplify it, so I will get this term lambda 1 square minus 6 lambda 1. So this is what the equation which is given, lambda 1 square minus 6 lambda 1. Again if I differentiate it, lambda by dou of lambda 1, which I will get 2 lambda 1 minus 6, which is equal to 0. Again if I simplify it, lambda 1 is equal to 6 upon 2, I will get 3. What is my lambda 1 value, which is equal to, what I am going to do is that, so I am going to substitute the lambda value to this equation, right? So here the x1 value which is 0 0, these are the initial points. This is what the newly calculated value, which is 3 for lambda 1, and so these are the s1 coordinate which we calculated, minus 4 and 2. If I multiply this, I will get minus 12 and 6. These are the coordinates. Now whatever the newly calculated coordinates, which I am going to compare with that, whether this is going to match with the 0 0. Now what is the optimal solution is that whenever we are reaching this point, optimum value which is 0 0, that is our optimum value. As per this given problem, with the output which we calculated here, minus 12 and then 6. So this is not the optimal value. In that cases, what we need to do that we have to repeat the entire process again. What is the initial coordinate? Instead of initial coordinate, now my the new coordinate value which will be the minus 12 and 6, and then if I repeat the process, I have to check at the end whether my result is 0 0. Else again I need to repeat this so many steps until I reach my the optimal value which is 0 0 or which is closer to 0. Again, so this is another example through which, right, how we can able to find out the optimal value, right, which is, so here this is the place where we will get the optimal value which is 0 0 here. This is the given which is the quadratic equation again, so that could be represented in terms of 0 0 again, the three dimensional representation equation which is 4x1 square and then 3x1 x2 plus 2.5x2 square and then minus 5.5x1 minus 4x2. So for the given problem, so now we can be able to construct this the optimal solution where, so we can reach the optimal solution whenever we are reaching the 0 0 coordinate. Now we will try to solve this mathematically. Now here this is what the example which is given equations. If I, this is f of f dash of x, if I differentiate the first the equation with that x1, so here I'll get 8x1. So this is what the equation which is given, 4x1 square 3x1 x2 and then 2.1 x2 square and then 5.5 x1 minus 4x2 square which is equal to 0. If I differentiate it, what the value I'll get. So here the first equation which is the equation which has been differentiated with the rho x1 in that. So here I'll get the 4x1 square, instead of 4x1 square I'll get 8x1 plus 3x2 and then minus 5.5, and then for the second term here this is the differentiation of the equation or f of x with the dou x2. So here I'll get plus 3x1 and then plus 5x2 minus 4. And for the same example, what I'm going to do is that I'm going to consider my learning parameter which is alpha. Constantly I'm going to consider which is 0.135. So this is my, I could say that this is my learning rate, right? My initial guessing values, whatever the things I'm going to identify is that, so we can select any random number which will be our initial value, and then from that place, right? So this is the place where I'm starting. That place I need to reach the center point, or where I could reach the down, right? So here if I substitute that x1 value x2 value in the equation, if I substitute 4x1 squared, x1 value is equal to 2, which is x1 square means again it is 4 into 4 16, very similar to that, plus x1 x2 value, so 3 into 2 into 2 I'll get 12. So if I simplify substituting x1 x2 values and then simplifying it, I'll get this my first f of x0 value which is equal to 19. Now what I need to do is that I need to substitute this value into this the given formula which is x1 is equal to x0 minus alpha. Alpha is the learning parameter and f dash of x0, and which, so if I substitute all the values, x0 value which is 2 2 and then minus, I mean the alpha value or the learning parameter value which is equal to 0.135, and then my x f dash of x0 which is equal to that whatever the equation which it derived, I mean after differentiating with the x1 and then x2 value. So right, that if I substitute my the x1 x2 value, I mean 2 2 in the equations, I'll get this. This is minus 2.275 and then 0.380. So this is the value. After that, if I simplify it, right, I'll get this f of x1 equal to which is 0.33, 0.399. If I construct this, if I draw this line here, this, so here this minus zero point 0.2 minus zero point 0.2 somewhere here and then 0.38 in the x2 value, zero point 0.3 somewhere here, I'll get this the 0.039. Right now what I'm going to do is that I'm going to compare this with whether it is equal to 0 0, else I'm going to repeat the process again. For that my next coordinate will be the same which I considered in the previous one, right? Minus 0.2 to 75 and then 0.380. Now I am going to repeat this process. Now my the alpha value which is not going to be changed, so that is going to be the constant value. My initial values are as per the second iteration which is minus 0.2275 and then 0.380, and then in the x1 x2 value if I substitute this minus 0.2275, again in the x1 1 value if I substitute 0.380, again I'll get this value which is 0.6068 and then 0.755. If I found this value zero point 0.6 in this x1 value somewhere here, 0.5, again. So here this is somewhere in the zero point 0.7. So here I'll get this value. So this is again minus 0.20841. So again this is also not the optimal value. Again I need to repeat this process in the third step. Again my coordinate will be 0.606, again 0.7556. if I repeat this process, again the x2 one value I supposed to submit 0.6068, again x22 I need to support this 0.7556. if I simplify it, I'll get this coordinate zero point 0.3 and then zero point 0.5. again if I draw it, again I'll get this minus 0.23. Now this has to be, again this is also not the optimal one, again I need to repeat. So at the end of this the step, right, I'll find which is the result which is almost equal with the previous one. The answers, what are the results I am going to get with the previous one. So here the previous step results point minus 2.33, again in the current step also which is minus 2.37, which is almost equal. So here the output, the optimal point which I am getting here almost the 0.55. So this is the final one through which we can able to find out the optimal solutions. With this we will complete our today's session, and the remaining things we will discuss in the upcoming lectures. Thank you.